So let's look at Saito's practice exam. And we'll look at question number 1A. So we're given, first of all, that the function f of x comma y is 2x squared plus y squared. And you know, I didn't actually print out the first page, so I don't know if he gives you anything on the first page. Does he give you any like equations or anything, or you're just on your own? Okay, on your own. So question 1A, find the linearization at the point 1, 1. And then there's some other stuff you asked, but let's just do that part first. So linearization at the point 1, 1. So great. So you have to remember the formula for linearization. The linearization of a function of two variables is going to be, and I'm just going to use the point that's given, f of 1, 1 plus the partial with respect to x evaluated at 1, 1 times x minus 1 plus the partial with respect to y evaluated at 1, 1 times y minus 1. If it was three variables, like if it was f of x, y, z, then you have L of x, y, z and be the function at x, y, z plus the partial with respect to x times x minus whatever plus the partial with y times y whatever plus the partial with respect to z times z minus whatever. Okay, so then let's find the things we need to fill in. I like writing the formula first and then kind of filling in the pieces after. So, because at least if I screw something up later on, the person reading my work can still be like, well, they knew what they were supposed to do and they made a small error. But if you just try to write like the answer without showing your work before then, and you make a small error, it's harder for someone to justify giving you partial credit. So make it easy for someone grading your work to give you points. So let's find f of 1, 1, no big deal. That's going to be 2 times 1 squared plus 1 squared, which is 2 plus 1. Fx is going to be 4x. So fx at 1, 1 is going to be 4 times 1. And finally, fy is 2y. So fy evaluated at 1, 1 is 2 times 1, which is 2. Now we throw everything into the linearization. So our linearization at x, y is going to be f of 1, 1, which is 3, plus fx evaluated at 1, 1, which is 4, times x minus 1, plus fy evaluated at 1, 1, which was 2, times y minus 1. And this is the answer to the first part of this question. Find the linearization. Great. We did the thing that was asked. You might even write words, is the linearization at 1, 1. Now, the second part of this part A question, which you could have made part B, but whatever. Use it to approximate f of 0.9, 1.1. So to approximate f of 0.9, 1.1, we're going to write, and I would encourage you to write this when you do this problem, is say it's approximately equal to L of 0.9, 1.1. That's the whole point, is you're going to plug that point into the linearization to approximate the actual function value. And the hope here is that it's easy to do. So I plug in 0. And again, one last thing here. Don't simplify this. Don't write this as 3 plus 4x minus 4 plus 2y minus 2 and then add all the constants together. We'll leave it like this so that when you see the subtraction, then the multiplication is easy. 4 times 0.9, yeah, it's not that hard, but 4 times negative 0.1 is easier to do, in my opinion. So here we're going to get 3 plus 4 times 0.9 minus 1 plus 2 times 1.1 minus 1. I saw someone on Discord doing this and like distributing the two here. That's fine, but the easier thing to do here is the subtraction first. So we're going to get 3 plus 4 times 0.9 minus 1 is negative 0.1. And 2 times 1.1 minus 1 is positive 0.1. And then we get 3 plus 4 times negative 0.1 is minus 0.4. 2 times 0.1 is plus 0.2. So 3 minus 0.4 is 2.6, and 2.6 plus 0.2 is 2.8. And he says compare it to the actual value. So I guess that means actually plug in the value to the actual function and figure that out too. If there's any clarification you need about what I've written, please don't hesitate to ask. I know my writing is not always easy to read. So plugging this into the actual function shouldn't be that terrible if we do a couple smart things. So f of 0.9 comma 1.1, sorry about that, is going to be 2 times 0.9 squared plus 1.1 squared. And although you might not know right off the bat what 0.9 squared is, I know you all know what 9 squared is. What's 9 times 9? So 0.9 times 0.9 is 0.81, right? It should be less than 0.9 because you multiply by number smaller. So we've got 2 times 0.81. In a similar way, 11 squared is, yep, 121. So 1.1 squared is exactly not that terrible. And then 2 times 0.81 is 1.62 plus 1.21, which is 2.83. So pretty close. Our linear approximation of that value was off by 0.03. Nice. Like, I mean, I don't know what, when they say compare, I don't think they mean actually find the difference. I think it's just like, say like, oh, look, see, they both are, and say, yeah, they're pretty close. The other point of a linearization is that it's supposed to be a good approximation for values of x and y or whatever near the point of linearization. So if we try to do somewhere else, and 2, 2 doesn't seem like to be that far, but it's going to be far enough that it's not going to be a great approximation. So let's see. Do the same thing. We're going to use the work we already had. So we're going to write down our same linearization here. I probably wouldn't even write it down again, but oh well. So our linearization is 3 plus 4 times x minus 1 plus 2 times y minus 1. And now if we plug in 2 to approximate f of 2, f of 2 is approximately L of 2, which is 3 plus, at this point, I might just write 4 plus 2, because I can see that 2 minus 1 is 1 times 4. But you don't need to show every little step if the arithmetic is pretty straightforward. But you can do this. 4 times 2 minus 1 plus 2 times 2 minus 1, which is 3 plus 4 plus 2, which is 9. Versus f of 2 is actually equal to, going back to the original function, 2 times 2 squared plus 2 squared, which is 2 times 4 plus 4, which is 12. Not that close. Right? Here's the difference of 3. The previous one is a difference of 0.03. It's a pretty stark contrast there, I would say. And so I will say the question just says, at which point is the linear approximation better? Describe your reasoning. This is probably where you should actually write out that the difference is better. So, right here, and here's probably the fastest way of writing it. The difference between our actual value and our approximation, f of 2 minus L of 2 is 12 minus 9, which is equal to 3. Versus in the previous problem, our f of 0.9 comma 1.1 minus L of 0.9 comma 1.1 was 2.83 minus 2.8, which is 0.03. So I would write something like at the point 0.9 comma 1.1, the linear approximation is much closer. I don't think you need to write more words than that. I think this is probably almost too much as it is, right? Anyone who can subtract can see the work you've done and be like, yeah, that number is smaller than that number. I don't think you need to write more words justifying that 0.03 is smaller than 3. But that's how you should decide which one's the better approximation, is that whichever one the difference is smaller, that's the better approximation. And sometimes I would just note, sometimes people throw absolute values around these just to make sure that the value is positive. So they might write it as like the absolute value of this minus this is that, which is 3. Here I subtracted in a way that guaranteed both things were positive. But if I subtracted in the other way, I would have put absolute values around it to make sure it ended up positive. Because we always like to talk about the difference as being a positive value. It's just easier to conceptualize. Sorry, you can't quite see the bottom there. Questions about any of that before we move on to problem 2?
Here's the true value.
Mhm.
Then the point at.
In actually putting into the function, which is usually not what we do, because usually the function is complicated enough that plugging in the given value is hard. Here, plugging in 1.1 and 0.9, we're on the just on the I say the precipice of being almost too hard. Like not too hard, but any like if it was the third power, 0.9 cubed, pretty challenging. 1.1 cubed, not that easy to do, right? Requires some writing down or something. But these were just at the edge of like, oh yeah, we can plug these in and figure it out without too much mental effort. Usually that's not something we do with the linearization. Usually we just use the linearization to approximate, and then we use a calculator to compare it to its actual value.
That was the next one. 1, 1.
No, they want you to actually compare the value.
Okay.
Yeah, they don't want you to compare it to f of 1, 1. They want you to compare it to f of 0.9, 1.1. At least that's my read of it. Let me double check. Nope, they mean right. It says then use it to approximate f of 0.9, 1.1, and then compare the approximate value with the true value at 0.9, 1. Yeah, no, that seems yeah. I think that seems. I mean, now I'm not 100% sure. Now that I read it back through my head, but that feels right. You plugged in, yeah. Yeah, because we're not. Yeah, no, I think I'm right. Because you plugged in 1, 1, you would just get, yeah, you would everything else would be 0. It wouldn't be interesting. So yeah, I'm gonna stick with that, but I'll look at the solutions just to be sure. All right. Yes.
So here we're just we're like finding the difference for like actually plugging into the function.
Right. So here's our linearization, our approximation equal to 2.8. And here's our actual function value at the point 0.9, 1.1 equal to 2.83. And we're saying, oh yeah, those are pretty close. Difference is 0.03. Whereas this other point here, 2, 2, which isn't that close to the point 1, 1, right? Because the linearization is at the point 1, 1. For this number that's not, for this coordinate pair that's not that close to it, we see that the linearization value equal to 9 and the function value equal to 12 are farther apart from each other. 3 is a pretty big difference when it comes to like numbers like this. So yeah, they're far from each other. All right. So everyone should, I'm not even going to write down the function, but I'm just going to say, so problem 2. I'm going to ask you a question before we do this problem. Find the direction or the thing that would give you the direction in which the function f of x comma y, I'm not even going to tell you what it is yet. I know you can see it, but whatever. Part A, find the direction in which this function increases most rapidly. At some point that I'm also not going to write down. And the reason I'm not writing down any specifics yet is because there is a general correct answer to this question. If I say, find the vector, find the direction in which this function increases most rapidly at the point, whatever, your answer is a one-word answer. The what? What is the direction that the function increases the most rapidly in? The gradient. That is the answer. The gradient. That is the answer. That is the direction. That is the vector in which the function increases the most rapidly at. So now we have to find the gradient and actually plug in the point. But if they say direction increases most rapidly, automatically you should think gradient. That is the answer. So our function is sine of x plus e to the xy. And our point is the point 0, 1. Okay, so now we find our gradient. So the gradient of f is equal to the partials fx comma fy, or however you choose to write it. You could do fx times I plus fy times j if you like the ij notation. Finding the partial with respect to x, the derivative of sine of x is cosine of x. The derivative of e to the xy is e to the stuff times the derivative of the stuff. And what's the derivative of xy in this situation? Correct. comma. Now the partial with respect to y. Derivative sine of x is 0, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and now the derivative of the stuff is exactly. And then we plug in the point. So the gradient evaluated at 0, 1. I'll remind everybody that sine of 0 is cosine of 0 is 1. Sine of 0 is 0. If you think about it, it's the right-hand point on the unit circle. The x coordinate is the cosine value, the y coordinate is the sine value, and you're over 1, and you haven't gone up or down at all. So it's 1, 0. So I would also, though, instead of if you just aren't sure, write cosine of 0. That's fine. At least they know you're doing the right thing. So I'm gonna be like, oh yeah, it's gonna be cosine of 0 plus e to the 0 times 1 times 1, comma 0 plus e to the 0 times 1 times 0. Simplifying this, we're gonna get cosine of 0, which is 1, plus e to the 0 times 1, which is also 1, comma 0 plus 0. So I get the vector 2, comma 0. Now, I don't know what he expects. I don't know if he expects you to write any direction vector as a unit vector or not. I typically would err on the side of writing as a unit vector. So here, the unit vector, the gradient divided by its own magnitude, is really easy to do when one of the components is 0, or I should say when all the components are 0 except for one of them. You just make the thing that you have left a 1 or a -1, depending on the sign. But here I'm going to have the vector 2, 0 divided by the magnitude of that vector, which is 2. If you've got over 2 and not up or down, the length of your vector is 2. I would still show the work, right? Still the square root of 2 squared plus 0 squared, but the square root of 4 plus 0 is just 2. So you have 2, 0 divided by 2, which is just 2 divided by 2, 0 divided by 2. I would say most people will probably be cool with either answer because they both point in the same direction, right? The vector 1, 0 is right there, and the vector 2, 0 is right here. They both point in the same direction. They both emanate from the origin. One is twice as long as the other, but they are still giving you the same direction. I would ask for clarity, right? I would ask him if he expects you to normalize or unitize any direction vectors or not. Okay. Part B, you should show no work for. If you had to do part A. The direction that the function decreases the most rapidly is turn around. So it should be either -2, 0, or if you prefer unit vectors, -1, 0. You're just multiplying your entire answer to part A by -1. I would even write the words opposite direction of most rapid increase. I should actually really, I should be underlining the increase part there because that's what it's the opposite of. Ooh, I like question 3. I feel like we haven't talked about question 3 type of things yet, or question part C here. Does not change. So the direction where the gradient is equal to what? I'm phrasing this incorrectly. The gradient shouldn't typically equal 0. It can if you're at a max or a min. But I shouldn't be asking about whether the gradient is 0. I'm asking in what direction is the change 0. And the gradient isn't the change. The gradient is the direction of maximal change. I'm looking for the direction for the directional derivative. Right? If I want the change to be 0, I'm asking in what direction do I go on my surface, on my mountain, so that I'm essentially like walking around the mountain, right? I don't want to be going up or down. I just want to be staying level. So I'm trying to find in what direction my directional derivative is equal to 0. Because the directional derivative is how much slope there is essentially. I will point out from these previous parts that in this direction, the directional derivative would have been 2. So the gradient gives you the direction of maximal change, maximal positive change. The magnitude of the gradient gives you the slope or the steepness. So if they said, what is the directional derivative in the direction of most rapid change? You would say, oh, it's 2. What's the directional derivative in the direction of most rapid decrease? -2. And finally, in what direction is not the gradient, but the directional derivative equal to 0? Let's just flip this piece of paper over. So we want to know, yeah, in what direction is the directional derivative equal to 0? Okay, so the directional derivative at the point 1, 0, which I don't usually like to write in there, but fine, is just your gradient at the point you're working with, dotted with the direction you're going in. So we can, we'll do it this way. So our gradient was, you can use either one. I'm going to use the 2, 0, 1 because that's the actual gradient value. So 2, 0 dotted with my unit vector, which I'm going to write as u1, u2, or xy, or whatever seems convenient to you. I would probably pick u1, u2. That needs to equal 0. I bet you can figure this out. We know how to dot these two vectors. In fact, you do this. Dot those two vectors together, set it equal to 0, and solve for whatever's left. Tell me, yeah. So it might be a little bit not arithmetically challenging, but conceptually challenging to figure out what your answer should actually be. Right, so dotting these together, the dot product of this vector and this vector, you're just going to multiply the corresponding components together. So you're going to get 2 times u1 plus 0 times u2 equals 0. 0 times anything is 0, so I really just get 2 times u1 equal to 0, or u1 equal to 0 divided by 2, which is still 0. Damn, that didn't tell me the whole vector. I don't know what u2 is. But it doesn't matter. If I picked u2 equal to 1 or 7 or 1,000, my vector would still point in the up direction. 0 in the x direction, 1,000 in the y direction. Or you could even pick negative 1,000 if you wanted to. Either direction would actually be technically correct. So 2 correct answers here. The 2 correctest answers are the vectors 0, 1, because I would like to write my answer as a unit vector, or 0, -1. So basically, thinking about being on the mountain again, and you're saying, oh, I'm going to go that way to stay level, or I'm going to go in the opposite direction to stay level. Because if I'm able to walk that way and stay level, I'm also able to walk backwards and stay level. Again, technically, your answer could be 0, 7 or 0, -5, but I think you should try to write answers as unit vectors, unless you are told you don't need to or have to. I certainly would. It's also really easy to do if one of your components is 0. Because if you want a vector of length 1 and one component is 0, the other component has to be the length you want, which is 1. Questions about any of that?
Yes, you can usually do like, do common zero, you can go to
Oh, I think anything, I mean, I think you should do what he wants you to do. So that's always the real answer, but has he even written any vectors on this test? I don't see any vectors. No, so I don't know. I mean, I would ask him. That's the real thing. You should ask, how do you want us to write our vectors? Do we need to write them a certain way, or as long as I'm consistent, is that fine? I would default to either the way I would default to this, but the other way I'd write this is, yeah, you could write this as u equal to, I would probably write it as 0i plus j, just to be extra explicit about it, but writing it as j would also be fine. Or u equal to 0i minus j. 1j. I don't want to write 1j, that feels silly, but yeah. All right. I would maybe imagine that the actual things you end up seeing on your exam might have vectors that have both components being not 0, like maybe a 3 comma -4 or something like that, where the magnitude is still relatively nice to find. It's a magnitude of 5. But I don't know. We'll see. I'll make up some problems that are similar to these, but maybe a little bit harder. All right, let's look at the following. Consider the following. Oh, there's a problem 3. Oh, sorry. Were there other questions about problem 2? So the reason we did the dot product is because the question was asking us, in what direction is, so they use different words. I interpreted that, but they said, in what direction does, so here are the words that I interpreted to mean this. So I got this, but the actual words that were written on the test were find the direction in which your function f of x, y, I'm not gonna write the whole thing. Find the direction in which the function does not change. Meaning, in fact, actually, IE is flat at the point 0, 1. That's what was written on the test. So I know if we want the function to not change, if you want something to not change, its derivative has to equal what? Right. So I said, oh, I need the direction so that the derivative in that direction is equal to 0. So the direction, which I'm calling the vector u, has to be 0. But then, how do we calculate the directional derivative? Oh, the directional derivative is always the gradient of the function dotted with the direction vector u. So that's how we're doing a dot product here, because that is how. Now there is another way you could. No, I take it back. This is the only way you can calculate. So dot product, you have to have the dot product being how you calculate the directional derivative. Once we knew we had to calculate the directional derivative, there was no choice but to use a dot product. Do I want to say those words? No, that's not really helpful. No, I will not say those words. Okay. Let's look at problem 3. Consider the following function. So consider, I'm going to write the function first. F of x comma y equal to x times cosine of y over the closed domain omega equal to the set containing x comma y such that negative pi is less than or equal to x is less than or equal to pi, and same deal for y's. Negative pi less than or equal to y, less than or equal to pi. And part A just asks us for local max, local min, saddle. So local extrema. Meaning you don't have to worry about any of this. So for this part here, yeah, you don't have to worry about this omega thing. I'm going to find the usual critical points, figure out if they're a max or min or a saddle in the usual way by calculating d equal to whatever and doing the usual thing. So I do this one relatively quick here. So let's find our critical points. So fx is going to be 1 times cosine of y. Set that equal to 0. Saying that equal to 0, so cosine of y equals 0 at either y equal to pi over 2 and y equal to negative pi over 2. There are lots of other values, but interesting. Yeah, I guess we do need to. So I guess we are limiting ourselves to this domain here because I don't want to consider every value ever because that would be an infinite number of choices. Let's find fy. Fy is going to be x times negative sine of y. Now, I'll point out that the only way that this first equation is equal to 0 is if y is one of these two values. So even though sine of 0 would be 0 and sine of pi would be 0 and sine of negative pi would be 0, that's not helpful because I can't have y be pi and pi over 2 at the same time. So even though y being negative pi, 0, or pi would make this equation equal to 0, I can't pair any of those points with any of these points because they're both talking about what y has to be. So my only critical points are where x is 0 and y is either pi over 2 or negative pi over 2. And if I'm incorrect in that we're not supposed to limit ourselves to this omega domain, then technically y could be any odd multiple of pi over 2. Right? 3 pi over 2, 5 pi over 2, 7 pi over 2. I might address that when we write the answer here, but we'll see. So let's find d. So d is equal to fxx times fyy minus fxy squared. Fxx is going to be 0 because fx doesn't have any x's in it, so its derivative is 0. Doesn't really even matter what fyy is. Also, when fxx or fyy is 0, it should mean you're going to get a saddle point, or it's going to be inconclusive because you can't end up getting something positive. Because you have 0 minus something positive will be a negative thing, or 0 minus 0 will be 0, and that's inconclusive. So 0 times I don't really care. In fact, I shouldn't even write anything there, but I'm going to. X times negative cosine of y. I shouldn't, but I can't. And then minus fxy, so looking at fxy, that's going to be negative sine of y squared. So then that's equal to just 0 minus sine squared of y. And then if I plug in my point, d of 0 comma pi over 2, sine of pi over 2 is 1. So we get 0 minus 1 squared, which is negative 1. And it doesn't matter if that was negative pi over 2 or if I plug in, if I plug in negative pi over 2, I get the same deal. I get 0 minus negative 1 squared, which is still negative 1. So both of these are saddle points. And that would have actually been true at every critical point, meaning if we were to extend this and say we're looking for a relative max, min, or saddles, and not limiting ourselves to this artificial domain here, then we would have also had a saddle point at 0 comma 3 pi over 2 and 0 comma 5 pi over 2 and 0 comma negative 3 pi over 2 and so on and so on and so on. Every odd multiple. Okay, let's look at the second part, because the second part is probably the more challenging part. Nice thing about the second part is you still need the first part. You still need this critical point. So for B, absolute max min. I really like drawing the domain. I find it helpful. So we're going as far as negative pi and pi in each direction. We got ourselves a little square here. And we already have 6 points to deal with. We know we're going to always have the corners test. That's just a fact of this situation. So pi comma pi and every other combination of pi and negative pi. And then we're also going to have any critical points we've already found as long as they are inside the square. So 0 comma pi over 2 definitely fits the bill. So does 0 negative pi over 2. Finally, and I would say finally, because I think it's the last thing you should check for, you have to check the edges. So I'll remind you that our function was x times cosine of y. And now we're gonna check each of these edges, which if it's a square or a rectangle, are really easy to do. Because this top edge here, this top line, is the line y equals pi. So set y equal to pi. If y equals pi, then f of x comma pi is equal to x times cosine of pi, which is negative x, because cosine of pi is -1. Oops, not negative x. All right. And then if you take the partial derivative, you're going to get -1, which never equals 0. Meaning you don't get any edge values. Here's what's really happening. On this edge here, from there to there, the slope is just a -1 slope the whole time. And so it's either going to be the endpoint here or the endpoint here that's going to be the highest or the lowest. You don't have to check any of the middle points because you don't have something that's like doing like this or doing like this. It's just going straight down. And I think we're going to get the same thing at y equal to -pi. So if y equals -pi, f of x comma -pi is also x times cosine of -pi, and cosine of -pi is also 1. So you get -1 times x. Again, you get the same result. The partial derivative is going to be -1, which is never equal to 0. Let's check the other edges. If we check x equal to pi, I think we'll get something more interesting. So f of pi comma y is pi times cosine of y. Take the partial derivative, you're going to get pi times negative sine of y. And if you set that equal to 0, you are going to get 3 answers. Because sine is equal to 0 when y is equal to 0 or plus or minus pi. But fortunately, 2 of those are already counted for. We already have pi and pi negative pi. We just need pi comma 0. X was pi, and we got y equal to 0. And then finally, I bet we're going to get negative pi 0 as well for the same reasons, right? In fact, let's just do this. And seeing that we're going to get that, we can make our lives a little bit easier. Be like, well, I could have said x was plus or minus pi, and then f of plus or minus pi comma y is plus or minus pi comma cosine of y. Taking the partial derivative, you get plus or minus pi times negative sine of y, and you still get the same zeros. So also minus pi comma 0. Look at all those 1, 2, 3, 4, 5, 6, 7, 8 points we need to check. Boo. Let's not. I'm going to leave that up to you because I do want to get to the problem that actually someone asked about before I said we should do the whole thing. So, but what you should do at this point is plug each of those into f of xy equal to x times cosine of y and see which one gives you the biggest thing, which one gives you the smallest thing. I don't know which one it's going to be, but I'm sure you can figure it out. I will say, well, here's also actually. Now I'll do it real quick. All 3 of these will give you 0. Because cosine of pi 0 or negative. Oh, no, sorry, that's a lie. Never mind. I don't know. You have to do it on your own. Do it on your own. It's good practice. Yeah. I would even write words like plug into f of xy and find biggest and smallest. Like, if at least if you're exhibiting that you know the process, I think that's worth something. If we have time, we'll come back to it. Well, let's do problem 4 because I think we probably won't have time. They'll probably take the rest of it. So use Lagrange multiply. Oh, and I did post. Oh no, I didn't. I will post. I did post solutions on Reddit or not Reddit, Discord to the homework 1, the Lagrange 1. I'll post them on Canvas too because I did do them both. Some of them both ways, just so you can see that there's 2 ways of doing it. Let's look at this though. So, sorry, number 4. We've got f of xy equal to e to the xy, and our constraint is x squared plus y squared equal to 1. So we want the gradient of f equal to lambda times the gradient of g. And I would say that g of x comma y is x squared plus y squared minus 1 equal to 0. You don't really need to do that, but it's pretty standard. Okay, so the gradient of f, let's do the x part. So fx equal to lambda times gx is going to give us fx, which is e to the xy times y, equal to lambda times gx, which is 2x. And then similarly, fy is going to be equal to lambda times gy, and we're going to get e to the xy times x equal to lambda times 2y. To me, it seems relatively clear that you're going to get x and y equal to each other, because if you interchange x and y, you kind of get the same thing. I don't feel like this is one where you really can solve for y and x in terms of lambda. Do you see what I mean? Like, I can't really get y by itself equal to something with just lambda in it. And that's the case. I usually go the other, I usually go the other way anyway. I would solve both of these for lambda, meaning I'm going to say that e to the xy times y over 2x equals lambda. And similarly, e to the xy times x over 2y equals lambda. Or you can go the fancy way and divide both equations. E to the x, so I'll just write it all out. E to the xy times y divided by e to the xy times x equals lambda times, yeah, no, that's fine. 2x over lambda times 2y. Those divide to 1. Those divide to 1. Those divide to 1. So you get y over x equals x over y. So you don't actually get y equal to x. You get y squared equal to x squared, which means you get y equal to plus or minus x. Similarly here, right? If I did the same work here, I have e to the xy times y over 2x equal to e to the xy times x over 2y. It is totally safe to divide both sides by e to the xy, or divide or cancel e to the xy's, because e to the xy can never equal 0. So it's okay to divide by it, because you won't be divided by 0. You're going to get the same thing. Multiply both sides by 2 times 2 over e to the xy gives us y over x equals x over y. Same deal. I didn't used to like this. I thought I was like, what are you doing? That seems kind of crazy. But the more I've taught this, the more I'm like, oh, that's kind of convenient, actually. If things look like they're going to cancel nicely, dividing the equations by each other is actually a pretty slick way of getting there. Not the only way to do it, though. So now that I've got y squared equal to x squared, I don't actually want to solve, I don't want to write y equals plus or minus x, or x equals plus or minus y. And the reason I don't is because I don't have just x or just y in my equation, so I don't need to. If I did have like x equals y minus 3 or something, then I would. But here I'm just gonna say, well, take my equation, x squared plus y squared equal to 1, and replace y squared with x squared. So I get x squared plus x squared equal to 1. So 2x squared equals 1, x squared equals 1/2, x equals plus or minus the square root of 1/2. Which you would probably want to rationalize as plus or minus 1 over root 2, or plus or minus root 2 over 2. Now, here is where we need to be a little bit extra careful. If x is positive root 2 over 2, y could be positive root 2 over 2 or negative root 2 over 2. Because y is plus or minus x. I know I didn't write that down anywhere, but look at it this way. If x equals positive root 2 over 2, then you're going to get y squared equal to root 2 over 2 squared, which means y squared equals 2 over 4, which is 1/2, which means y is equal to plus or minus the square root of 1/2, which is the square root of 2 over 2. So if x is positive, y could be positive or negative. And similarly, if x is negative, you still get the same result. Y could be positive or negative. So there's actually 4 critical points here. There's 4 values that satisfy the situation. So we get x comma y equal to root 2 over 2 comma root 2 over 2, or root 2 over 2 comma negative root 2 over 2, or negative root 2 over 2 comma root 2 over 2, or negative root 2 over 2, comma negative root 2 over 2. Now we should go back and actually figure out what's the question asking us to find. Use Lagrange multipliers to find the maximum and minimum values of the function. So we've got points that are critical points that will either maximize or minimize our function, potentially. Let's plug them in and see what happens. So f of xy equals e to the x times y. I'll remind you, if you think about the e to the x function in your head for a second. What is just good old e, or you can look to your right hand if you want to. E to the x, draw it in the air. Everybody draw it in the air for me. Draw some e to the x in the air. Good. Yes, good, good. It goes like this. It's increasing from left to right, meaning the larger the power is, the larger the output is. The smaller the power is, the smaller the output is. So we just really have to compare which powers end up being the biggest based on this. So I plug in root 2 over 2, comma root 2 over 2. I get e to the root 2 over 2 times root 2 over 2, which is 2 over 4, which is e to the 1/2. Which other point is also going to give me e to the positive 1/2? The positive negative, the negative positive, or the negative negative? The negative negative. This is also equal to f of negative root 2 over 2, comma negative root 2 over 2. Do we think the other 2 points will yield the same value? Not the same as what I've written, I mean the same as each other. I think we do. Let's find out. We do f of root 2 over 2, comma negative root 2 over 2. We're going to get e to the root 2 over 2 times negative root 2 over 2, which is going to be e to the negative 2 over 4, or e to the negative 1/2. And that will be the same as if we do f of negative root 2 over 2, comma root 2 over 2. Okay, so now let me ask you all an important question. If I said for you to tell me what is the maximum value of this function, what's the answer to that question? Is it root 2 over 2, comma root 2 over 2? Is it negative root 2 over, comma negative root 2 over 2? No, it's neither of those things. That's where the maximum occurs. What is the maximum value we get when we plug in the point where the maximum occurs? On the page. Thank you. E to the 1/2, or if you like, the square root of e is the maximum value of f on the circle x squared plus 1. X squared plus y squared equals 1. Similarly, e to the negative 1/2, or 1 over the square root of e, is the minimum value. We don't need to say that it occurs at multiple points, although it does. We just are writing what it is. So do be careful when you're asked to find where a maximum occurs versus what the maximum is. Those are two different things. The maximum occurs at the point root 2 over 2, comma root 2 over 2, or negative root 2 over 2, comma negative root 2 over 2. The maximum value is what you get when you plug that in, which is e to the 1/2. All right, it is just about 2 o'clock. My plan before Wednesday is to write up a test very similar to this with different questions, probably a little bit harder, and post it to Canvas before then. We can go over that. I'll try to also do, I feel like you all want to see a couple more Lagrange multiplier examples, so we'll do that on Wednesday as well. If you think of anything you want to see on Wednesday, you can also email me or just let me know in class that day. Don't spend all of your effort on Lagrange multipliers. It's only going to be like a quarter of your test. Spend effort, but I think it spells it out, right? Linearization, directional derivatives and gradient, finding local max and local min on a closed and not closed interval, and Lagrange multipliers. And also, it looks like you better know how to find trig functions, right? You better know how to do what cosine of 0, sine of 0, all that jazz. It seems like I wouldn't have put these examples on the practice exam if I didn't expect my students to be able to, like, if I wasn't planning at least somewhere putting some trigonometry on my test. All right, all I got for today. I'm gonna go over to C class and have office hours. You're all welcome to come on over.